In this lecture, we will be covering the topic of extrema of functions. So the first definition out of several, we'll have a lot of terminology in this lecture. If C is in the closed interval AB, then f of C is the minimum value of f of x on closed interval AB if f of C is less than or equal to f of x for all x in AB. So this helps to look at the picture. And this is the specific case of looking at a continuous function on a closed interval. Now remember, if we have a continuous function on a closed interval, when we draw it, we put the pen down, we draw the function without taking the pen off the paper until we get to the end of the interval. Now in this case, the minimum value of f on this interval AB is nothing other than its lowest point. So using this terminology here, this would be our minimum value of f of C described here. And you see from the definition that f evaluated at C is less than or equal to f of x for any other x in this interval AB. So that's formally what it means for f of C to be the minimum of f on this closed interval AB. For the maximum, you just go in the other direction. So for the maximum, we would have its highest value, and here we have it occurring according to the terminology in the definition at D. And so this would be the maximum value of f on this interval. And you see that the defining criteria is that f of D is larger than or equal to f of x for any other x in AB. Again, thinking of that as just meaning it's the highest point. So this is the minimum. F of D is the maximum, and f of x is always in between its minimum and its maximum on our interval AB. Now, this is just the definition of minimum value and maximum value on a closed interval. But we can go a step further. And we can use this max-min value property. If we have a continuous function on AB, then there exists a C and a D such that f of C is the minimum value and f of D is the maximum value of f on AB. So in other words, f has to achieve both a minimum on AB and a maximum on AB. And again, intuitively, this comes from the idea that when we draw the graph of our function on AB, we have to draw it without, once we put the pencil on the paper, we can't take it off. And that nature of this having no jumps, no holes, and no vertical asymptotes on AB forces the function to have both a minimum and a maximum value on this interval AB. And it's worth pointing out, functions like this, defined on closed intervals, come up a lot in applications. It's generally the case that your independent variable has some closed interval that you get to choose from. So, for instance, if you had some function, say, of time, where your clock runs from 0 seconds to 10 seconds, that has your function defined on a closed interval. If you have a function of, say, economic inputs, say you're in production and it's a number of pounds of salt in a recipe, you're also picking from a closed interval, usually from 0 to some large number of pounds of salt. So this comes up a lot, and this is an extremely handy property. So let's look at some examples and see how this works. One example, here we have a linear function. So we have y equals x plus 2. On the interval 1, 4. Well, we know y equals x plus 2 is just the function y equals x shifted up 1 unit. So it has this y-intercept of 2. So we know this is what our function looks like. And we're concentrating on this function on the interval 1, 4. So we're concerned with our function on this interval here. And we can see, just from visual inspection, that the minimum value occurs at this left endpoint. So our minimum value is f of 1, which is 1 plus 2, or 3. We also see the maximum value happens at an endpoint, in this case, the right endpoint. So our maximum value is f of 4, or 4 plus 2, which is 6. So this is just one simple example, the case of this linear function. And we see in this case of a linear function, the endpoints give us the maximum and the minimum values. When your function's linear, that will always be the case, by the way. We'll look into a more general continuous setting soon, but for the time being, we see that your minimum can happen at an endpoint and your maximum can happen at an endpoint. How about another example? Let's think about this function. Here we're working on the interval 0, 2. So in this case, we know our function looks like this. And again, we're working on the interval, and the closed interval 0, 2 in this case. But things are a little different here. We know we have this asymptotic behavior near the line x equals 0. It's actually a vertical asymptote. So the function is defined here at 0. 0, 0. But again, in this case, we're confined to this closed interval 0, 2. And we can see that it is the case that we have a minimum value. It happens at the right endpoint. So that's f of 2, which is 1/2. So the function does have a minimum value on the interval 0, 2. But note, there is no maximum value. This function is unbounded. Well, what's the difference between this and the previous example? Well, notice that the function is not continuous on this interval. So f is discontinuous at x equals 0. In particular, it has a infinite discontinuity, an asymptote, vertical asymptote. If we go back to our theorem for the min-max value property said we were only guaranteed that f achieves a minimum value and also a maximum value on a closed interval AB if f is continuous. If it's not continuous, we do not have this guarantee. This example is an illustration of that. Because the function is not continuous and has this vertical asymptote of x equals 0, we actually see that this function does not attain a maximum value. That theorem does not apply. Okay, well, we've now talked about this idea that if your function is continuous on AB, it has a minimum on AB, and it has a maximum on AB. Where does that happen? In the first example, we saw the case of a linear function where the minimum on the closed interval happened at an endpoint and the maximum happened at an endpoint. But we can imagine things working out a little bit differently. Perhaps we have a function that's defined on this closed interval AB, and maybe its minimum happens at the left endpoint. So we see the minimum here, which we're calling f of c. So in that case, our c, where the minimum occurs, is the left endpoint. But this time, we have a peak here. And this will be our d. And so this is our max, which we're calling f of d in our terminology. Now the big difference here is that this was not an endpoint. So the minimum happened at an endpoint, the maximum happened in the interior of AB. So we need to give this situation a name. We need to give this kind of point a name. And we call it a local extrema. In this case, we would call it a local maximum value. So let's get into the definition. We say that f of d is a local maximum value of f if f of x is less than or equal to f of d for all x, and this part's key, in some open interval containing d. That is the part that defines the local nature of this maximum value. So for example, if we draw a function think about this peak here. This is a peak. If you think of this as the skyline of a mountain range, this is still the top of a mountain, but it's not the highest peak. But it's still a type of maximum value. And the definition is that it's a local maximum value, because if you take that point and then you come down here and you choose just values in this interval, all that matters is that there is some interval around here, around our d. This is a local maximum value as long as we have such an interval, such that for any other x in that interval, f of d is bigger than or equal to f of x. So when we restrict the function here, we see that with that restriction, this f of d is the highest value. That's what it means for this point to be a local maximum value. It doesn't have to be the maximum of the whole function, that has a different name, the global maximum or the absolute maximum. It just has to be a maximum in its own little neighborhood. And you can see in this picture that we have multiple local maximum values. Every peak qualifies as a local maximum value. Once we understand the concept of a local maximum value, local minimum value is the natural equivalent, except it's the valleys. So the bottoms of the valleys give us a local minimum, our local minimum values. So for instance here, according to our definition, we say this f of c so at c, we have our local minimum value of f of c. If, for some open interval containing c, so down here, in that interval, c is the minimum. And again, we come up and we see that with the function restricted to that interval, c is in fact a minimum. So it satisfies that minimum criteria locally to this interval containing c. And again, it doesn't matter how big this interval is. It can be really tiny. As long as you can find one, it's a local minimum value. We have the more general encompassing terminology. A local extremum of f is a value of f that's either a local minimum or a local maximum. So all of these points, orange and blue together, would constitute local extrema of f. Now we did draw this in a way where the function was differentiable. It doesn't have to be. You could also have local extrema that look like this. So using our same color coordination, we would have a local maximum at that point. And we would have local minima at these 2 points. So we don't necessarily require the function to be differentiable for a local extreme value to be defined. That being said, as students of calculus, we tend to think a lot about differentiable functions. So if we have a function f that's differentiable on an open interval containing c, if c is a local extremum of f, then f prime of c equals 0. And we can see this. So if we think about that kind of picture that we just drew, so now our function is differentiable, so we have to draw it in this smooth way. And think about having those types of extrema. So those were our local maximum values. And then we had our local minimum values. And note what happens at each one of these points. Note that the tangent line is horizontal at every one of these points. So the tangent lines, or the tangent line at a local extrema of f is horizontal. What does it mean for the tangent line to be horizontal? Well, then that's none other than the derivative of the function being 0 at that point. So it's always the case that if your function is differentiable and it has a local extreme value, be it a local maximum or a local minimum, the tangent line has to be horizontal at that point. This is a theorem that we will prove. It comes quite quickly from the definition of derivative. So, suppose f of c is a local maximum value of f. Since it's differentiable, we can look at f prime of c. It exists. Since f prime of c exists, the definition of derivative means the one-sided limits are equal. The one-sided limits from the definition of derivative. So the limit as h goes to 0 of f of c plus h minus f of c over h, that is the definition of the derivative of f prime of c. But what we're going to do is note, let's come from the right. And since the limit exists, because it's differentiable, this has to be the same thing as the limit coming from the left. And so we'll focus first on the limit come from the right. So consider h going to 0 from the right, which means h is positive. F of c is bigger than or equal to f of c plus h for h small enough. Remember, f has a local maximum value at c. So our function at c has to have some interval around it where it is above the function evaluated at any other point in that interval. So again, this is because f of c is a local maximum value of f. Well, take this, subtract f of c from both sides. That tells us f of c plus h minus f of c is less than or equal to 0, right? Bringing this f of c over, you get 0 is greater than or equal to f of c plus h minus f of c. Well, h is greater than 0. That's what we're focusing on, the right-hand limit. So that means f of c plus h minus f of c all over h is also less than or equal to 0. Okay, now take limits of both sides of this inequality. As h goes to 0, again, we're going from the right because h is positive. When we do that, we get the limit as h goes to 0 plus of that difference quotient, f of c plus h minus f of c all over h, is less than or equal to the limit as h goes to 0 plus of 0, which is, of course, just 0. There's no h involved in this 0 term here, so that limit is just 0. But we also note that this is f prime of c by definition of derivative. So what we just showed, look at this string of inequalities. F prime of c has to be less than or equal to 0. That's the first step. We then can go through the same kind of procedure. So we repeat for h going to 0 from the left. So in that case, h is negative. The same type of reasoning will give you a result here, except the inequality will go the other way. Here we find f prime of c is greater than or equal to 0. Well, if f prime of c is both less than or equal to 0 and greater than or equal to 0, the only way that can work is if it is equal to 0. The only way that this inequality can hold is that this f prime of c equals 0. And that concludes the proof. So this proves, in the case of a local maximum value, that the tangent line to f, to the graph of f, at that value is horizontal, as demonstrated by this derivative at this local maximum being 0. So coming back to the picture here, remember, our tangent line had to be horizontal. So that proves this theorem, and this is a really key and important theorem. And now let's think about how we use it, and we use it in the following way. We use it to find local extrema of a differentiable function f. So the procedure to find local extrema when your function is differentiable, set the derivative of the function equal to 0 and find all the x that satisfy that. So the kind of picture that we drew before, we had all of our local maxima, right? We had horizontal tangent lines at our local maxima. And then at our local minima, we also had horizontal tangent lines. The point is, f prime of x equals 0 at every one of these points. So if a point is a local extrema of f, f prime of x, we'll say if a point C is a local extrema of f, then f prime of C has to equal 0. That was our previous theorem. So the way to find the set of candidates for local extreme values is done by this procedure. Set the derivative of f equal to 0 and see where it actually works. Now, that being said, we should notice the converse of this theorem is not true. If f prime of c equals 0, f of c is not necessarily a local extreme value. So the converse of our theorem is false. So specifically, if f prime of c equals 0, f of c need not be a local extremum. And the counterexample we use to argue for this is a pretty simple one. F of x equals x cubed. Let's think about finding local extrema. F prime of x is 3x squared. We set that equal to 0. That only has the solution of x equals 0. But the graph of our function, y equals x cubed, we know looks like this. So it is true that the tangent line is horizontal at x equals 0. But it's also true that the origin is not a local extreme value. So f of 0 is not a local extremum in this case. You can see that if you go to the right, the function goes up. That means it can't be a local minimum. That means it can't be a local maximum. If you go to the left, it goes down. That means it can't be a local minimum. So it's neither. So the idea behind using that theorem, when you want to find local extreme values for a function, setting f prime of x equals 0 gives you candidates for that. But it does not necessarily give you or guarantee you to find local extreme values. If the local extreme values happen, they will solve f prime of x equals 0. But f prime of x equals 0 does not imply that you have a local extreme value. And this is the classic example of that. We will see this in action much more as we continue our treatment of extreme values of functions in part 2 of this lecture.